All right, thanks for joining. This is chapter 2.2, graphing equations. So the objective is to sketch graphs of equations and graph and their characteristics. So the graph of an equation in two variable x and y. So you have your x, y, Cartesian plane here. Consists of all the points on the xy plane whose coordinates x comma y satisfy the equation. So if I have some equation here, let's say y equals something, okay, all of the points on that line, so say this point x comma y and this one or this one, all these points would make this equation over here true. So that's why we can graph equations. It's every point to make this true. So even decimals and fractions and all those numbers in there. So ways to graph equations. We will make a table, which is probably the very first thing that you ever did. We will look at the intercepts. Know the parent function. So this is where we're going with this. This will be a must. Use the graphing calculator. And then a lot of times we just use the combination of maybe these two normally. So graph the equation. 2 equals, or y equals 2x minus 1. So let's just go back to the table here. This is the way that you probably did it first in maybe algebra. So we'll just pick some x values. So let's say -3, 0, and 3. So if I plug in -3 into this equation, we'll have 2 times -3 minus 1. So it's -6 minus 1, -7. So the order pair -3, -7. Right there. 0. So 2 times 0 minus 1, minus 1. So I have 0 minus 1, and then 2 times 3 minus 1 is 5, so 3, 5. And so I have that linear graph right there. But you can also see that this is y equals mx plus b, which is a line. Another way we can graph it is just knowing the parent function. We start at b, which is my y-intercept, and I use the slope, which is 2 over 1, so up 2, right 1, up 2, right 1, up 2, right 1, or I can go down 2, left 1, okay, and get those points. So graph the equation, y equals x squared minus 5. Again, we will make a table. -3, 0, 3. And it doesn't have to be those points. You could choose any. I just like to choose a negative and a positive, and I always like to choose 0. So we have -3 squared minus 5. So that's 9 minus 5 is 4. So -3, 4. 0 squared minus 5 is minus 5. So 0, -5. 3 squared minus 5 is 4. Right there. Guess so that looks like that. So I've got a parabola. You notice up here, that's the parent function x squared forms a parabola. So I've got that u. The -5 is actually ends up being the y-intercept. Okay, but the table works really nice for that. And if I don't know what something looks like, such as this one, okay, I'm unsure what that is, we can choose more points. So let's try by doing a table. One and two. Now let's choose more points. So x to the third. So -2 to the third minus 8. -2, -8. Negative 1 to the third is minus 1. 0 to the third is 0. 1 to the third is 1. 2 to the third is 8. So I've got this weird looking graph in here. It kind of looks like this little crab. Okay. And we have, with this kind of our progression of graphs, let me just do it on the back here. I call this the evolution of polynomials. Okay, and we'll start with a constant, y equals c. It's a line like that. We have some line y equals x. Goes right through there. And we can have y equals x squared. This is that. So now we get into the polynomials. Like that. Or we can do it like that, which is going to be more helpful. X to the fourth. X to the fifth. And hopefully you're seeing here what's happening is we're just adding in some extra humps in here. This would be to the third, fourth, fifth, sixth, seventh. So you have to the first, second, third, fourth, fifth, sixth, seventh. And it doesn't have to have all these humps. Okay? And x to the seventh, or yeah, an x to the seventh could look like this. Okay, it could look something like that on your calculator there. So when a graph touches the x or y axis, that point is said to be an intercept. If we look at the x-intercept, that is where my graph crosses the x-axis. Now, at that point, we'll have some x-coordinate, but y-coordinate, we're on this axis, so my y-coordinate is 0. So the x-intercept is also when y equals 0. For my y-intercept, that's this point right here. It's where the graph crosses the y-axis. So we have some y-coordinate, but your x is 0. Okay, and that's how we find it. We will use this part. We'll use this part to help us find them. All right, so if we look here, so find the intercepts of y equals x squared plus 1. So if I look for x-intercepts, that will be x comma 0. So we're going to plug 0 in there for y. Plus 1. So minus 1, x squared equals minus 1, square root, x equals plus minus I. Well, what does that mean? That means there are none. They're imaginary. There are no x-intercepts. So y-intercept will be in the form 0 comma y. So plug 0 in for x. So you get y equals 0 squared plus 1. Y equals 1. So my y-intercept would be 0 comma 1. My x-intercept is none. Why is it none? Because I got an imaginary solution for that. So symmetry. Symmetry means to be balanced around some object, a point or a line is what we're going to look at. So we have the x-axis, y-axis, and origin symmetry that we're going to look at. And if we look at this graph here, this one, and if I take a point, let's say right here, and match it with its exact point over here and connect them, they go through the origin, making this the same distance as that. Okay, that's what we mean by symmetry. I can match all of these to their matching points and they'd be the same distance away. Okay, so this one has origin. This one here, if I trace it out just a little bit to make it a little bit darker, if I take this point, map it to this point, those two distances are the same. So that one has a symmetry about the y-axis. And this one actually has, I don't know, 1, 2, 3, 4, maybe 4 or 5 different graphs on it. So let's just look at one right here. So if I look at this one, okay, if I take it and map from here to here, or here to here, or even here to here, they create a bisector. So this line right here, that x-axis is a segment bisector of each one of those. Okay. So without the picture, how do I test for symmetry? You're going to want to know this, so note it. So x-axis symmetry, replace the y with negative y, and the equation doesn't change. So remember we talked about, let me just move this over here. We talked about here that if I have a graph here, that all the solutions on here have the same equation. Okay, so just for instance, that's the equation. Oh, you can't see that. That's the equation for this part right here. So all these ordered pairs satisfy this equation. They make it true. Well, if I take this ordered pair right here, that's x, y, and if I map it through that over here to x negative y, the equation hasn't changed. It's still the same equation. So if I plug in from y, plug in negative y, I get the same thing. Hence x symmetry. I do the same similar thing with y symmetry. So y-axis symmetry, replace x with negative x and the equation doesn't change. Origin, replace x and y with negative x, negative y, and the equation doesn't change. If some of you remember back from geometry, we had transformations, and one of them was 180-degree rotation, which is this right here. Well, 180-degree rotation actually takes it and reflects it through the origin. So if I rotate this around 180 degrees either way, I get that symmetry through the origin, which is the same as what we set up here. Okay, so if we look at one, just test the equation for symmetry. Okay, so we'll look at x-axis. In order to do that, we take y. We'll take a y and plug in negative y. Negative y times negative y is y squared equals 3. So notice the equation didn't change, so it does have x-axis symmetry. So then y-axis, we leave y alone, but now we change x to negative x. Well, negative x to the third is the same as negative x to the third. It's still negative. So now that this equation is not the same as this one, it does not have y-axis symmetry. Origin symmetry, we change both of them. So negative y squared equals negative x to the third. So this is y squared equals negative x to the third. So those aren't the same. They're in there, so it's a no. Now you may be thinking, well, does it have to have x-axis and y-axis to have origin? Yes. Okay, so if these two are yeses, then this should be a yes. But we always like to double check. Determine the type of symmetry for the equation. So x-axis, we'll change y. So I have negative y equals x squared plus 1. So these are not the same. So no. Y-axis, we change x. So y equals negative x squared plus 1. Reduce it. So negative x times negative x is x squared plus 1. So those two are the same. So yes on the y-axis. Origin, we change both of them, but you probably are guessing that it will not. So negative y equals x squared plus 1. Since the original and this is not the same, it does not have origin. All right, so x-axis again. That's negative y to the third plus 1. So it's negative y x to the third plus 1. So that's a no. Y-axis, we plug in negative x with y equals negative x to the third plus 1. So those aren't the same. And then origin. So negative y equals negative x to the third plus 1. So it's negative y equals negative x to the third plus 1. So that is not the same. Okay. Now careful, because sometimes we could get negatives all the way through here and divide by that, then it would. But this one is no. And actually this graph looks something like this. Okay. So does it still have, it still has symmetry, okay, but the symmetry is actually about this point right here, not the origin, because I've shifted it up. So if I'm at from here through there to here, those would be the same. Okay. And we're not worried about finding that. We're just looking at these three specific symmetries. Okay, use both intercepts and symmetry to graph the equation. So this is an equation you've probably never seen before. Okay, so let's look here at the x-intercepts. So that's x comma 0. So that's x squared plus 0 squared equals 25. X squared is 25. Square root, x is plus minus 5. So I have 5 comma 0, negative 5 comma 0. So I'm just going to start my graph over here. So my x-intercept is at negative 5, and 5. Y-intercept, that's 0 comma y. So that would be 0 squared plus y squared equals 25. So that's nothing. Square root, y equals plus minus 5. So you have 0 comma 5, 0 comma minus 5. So there's 5 and there's minus 5. Okay, now let's check for symmetries. So if we look at x-axis, we'll plug in negative y. So I have x squared plus Negative y squared equals 25. Negative y times negative y. And you might now be asking yourself, well, if it's an even power up here, will it be positive? Will it be the same? Yeah. If it's even up here, you will have a positive. If this was like 3, 5, 1, 7, some odd number, this would have changed to a negative. So it's the same. So we do have x-axis symmetry, y-axis. You plug in negative y4, or you plug in negative x. So that's x squared plus y squared equals 25. So that's also a yes. And origin, hopefully you're saying yes, because it's both of these. Let's just check. We'll plug in negative x. We'll plug in negative y. Whoop. So that's x squared plus y squared equals 25. So that's yes. Okay, so this is perfectly symmetric. Okay. Now it might be helpful to find some more points on here. And if I take this equation, maybe write it this way, you'll notice that that's a Pythagorean theorem. And there's a very important Pythagorean triple that says 3 squared plus 4 squared equals 5 squared. Okay. So I'm at the order pair 3, 4. So 3, 4. But remember, it's symmetric about the y-axis, so that same point lies over here, and it's symmetric about the x-axis, so those 2 points can come down here. I can also switch these. I could say 4 squared plus 3 squared equals 5 squared. I just flip-flop those. So that's here. I reflect it over here, and I reflect those 2 down here. And hopefully you notice that we created a circle. And here's my 3, 4, 5 right triangle from down there. Okay, so a circle is kind of related to that triangle, and that's kind of dealing with some trigonometry stuff there. Okay. So here's your suggested problems. From 2.2, I believe I had a challenge problem. And let me find that challenge problem here. I think it was number 89. Number 89 would be your challenge problem. Determine whether the graph of that has any symmetry. Okay, so if you got questions, please let me know. As always, thank you for watching. This is at THS Mr. Jones signing off.